Hi, my name's Tim Comyn. I'm going to give a talk today on the commercialisation of high temperature piezos. The materials that Tim talked about earlier that came from the University of Leeds, we spun these out into a company and started commercialising these some time ago. Paul asked me today just to talk a little bit about how that happened. So I'm just going to split this up into a couple of bits. I'm going to talk about markets and sectors a little bit, and the same as Paul did, but perhaps drill into those a little bit more to give you an idea of why we think it's so important to have some materials which work really beyond where PZT does today. And then I'll talk a little bit about ionics, how we've engaged with the market, and really the barriers to be able to work with high temperature piezos. There's a lot more the metrology that's going on here, understanding the properties. There's much more to make these a viable product, with some case studies as well. So the market sectors, it's difficult to get data on this. This is about 4 years old now, and it's considered that the market for all piezo materials is something like $15 billion. The majority of that is PZT. For high temperature piezo market, how big is the piezo market for high temperature materials? It's difficult to get a handle on that. We've done quite a lot of market research ourselves, really over the last 3 or 4 years, talking to key sectors. We estimate it's something like 500 million, so it's a lot smaller than the PZT market in its entirety. It's quite spread out and diverse, so its current applications, its new benefits. I don't think with a new material system, we're not looking to replace existing stuff, we're looking to generate new markets. And there's conversion of alternative methodologies. So it's very fragmented. Just go through these a bit more detail. So the main focus for us is process and plant. This is where we started really in steam measurement. Steam is used for lots and lots of different sectors. The benefits are energy and money mainly. To give you an idea of the scale of this, a steam trap, of which there can be 10,000 in a petrochemical factory, which break on average every 10 years, undetected, will hemorrhage €5,000 of energy every year. So in something like an oil refinery where there's 10,000 traps, there's a huge amount of money being wasted. Nuclear, there's going to be a poster by Marco Budimir from Initech, I think, during the session. Nuclear, lots of shutdown, it's been in the news. Kit's getting older. To keep a license running longer, there needs to be much more measurements. So there's two real temperatures for steam. One's around 350, which can't be engaged by PZT. There's other applications up at 850, depending on the application. To give you an idea of what unplanned shutdown costs for a combination of nuclear and conventional power stations, it's 23 billion euros a year for unplanned shutdown just in Europe on its own. And 10% of that is considered to come from steam. So there's massive benefits. It's obviously pound signs, but it's safety all of a sudden. There's some big risks from having things happen that you didn't know were going to happen. And lots of reasons why you want to do that. Really, it's failure, but it's efficiency as well, stress cracking and corrosion. Oil and gas. Paul mentioned oil and gas. It's getting deeper, it's getting hotter. So the reserves to the north of the UK and the Shetland Islands are now at 10 kilometres and 240 degrees centigrade. So that's 100 megapascals and 240 degrees centigrade. PZT can't survive that. Aluminium can't survive that. These incredible, incredible pressures. Geothermal's coming online now, in Germany, certainly, and that's at 300 degrees centigrade, fracking, lots of sectors which have been attracted by oil and gas. So the benefits of productivity, but there's also a safety aspect to this as well. BP are committed to getting rid of manual inspection entirely of their high pressure lines by 2020. And to do that, they need to have continuous monitoring from sensors which are deployed over lots of different plant types, over lots of different regions. So there's downhole, there's upstream, there's downstream. There's lots of different oil and gas applications. Aerospace, this is really where we've had a lot of experience in my sort of university, in my career life. The cost savings from a tiny increase in performance in an aero engine is incredible. An Airbus burns something like £10 million a year. So there's cost benefits from having a lot more control. Certainly in the injectors around here, this is too hot for most piezos to operate, back at the high pressure turbine. But in the compressor, 400 degrees centigrade, direct injection of gas, of kerosene is on the horizon, certainly on the west coast of the US. There's legislation coming online for that now. So it's about faster control, but it's also about making things lighter. If you've got sensors which are smaller in the high temperature region, you've got less harnessing. If you can make the engine lighter by doing things more efficiently, an engine which is lighter by 1 kilo is worth $600 more, just because that's the amount of energy it will save in its future. There's lots of applications there. But automotive, big renaissance with the diesel fuel injector in Europe, certainly, NOx sensors, turbo diagnostics potentially coming online, and a lot of that's around energy savings as well. So there's generic benefits of a high temperature piezoelectric technology that will go above what you can manage with PZT at the moment, 200 degrees centigrade plus. There's opportunities, health and safety, productivity, energy, but at the end of the day, it all comes down to money. Perhaps one comment to bring out with all of these sectors down at the bottom is many of them are very, very conservative. So you don't just suddenly develop a product and start putting it in a gas turbine. It can be 7 years before there's in-flight tests, so very, very conservative. So we believe there's a need for a new high-temperature material. High-temperature materials exist, clearly. There's the titanates around, the langossites, quartz itself. I think what our angle is really is something that can plug and play with PZT. So that's where the Onyx materials have been positioned really. Comparable D33s with PZT, but a higher operating temperature. I think it's fair to say there's competition with things like the business Scandate families, which have come out of TRS in the United States. But scandium oxide is phenomenally expensive, variable, and there's a security supply. It's mined in Russia. I think it's single source. So I'll just talk about the company really and where we started. We formed the company in 2011, quite some time ago now when we look back. And our initial engagement was with steam processing. We engaged with the leading steam company in the world, really to look at their failing traps and put simple devices on plant for them. We filed a patent in 2012 in a multi-region. It's busy limping through those as we speak. It takes a very, very long time. 7 years ultimately, I think, until we've got all of those sectors covered, if possible. We identified a CEO and got investment in the dying hours of 2013. Last year was very much about building up a team, engaging the markets that we needed to do. And just on Friday, I managed to secure the next big investment, which will allow us to generate dedicated premises, increase the team considerably. There's 7 of us at the moment. It will allow us to double the size of the team and really give us comfort for the next 2.5 years. And this is how we've gone about exploiting this material. So, as Tim talked about, our original IP and our strengths, I'm a material scientist, are in the raw materials here. So we know how to make these ceramics, we know about electroding, we're comfortable with all the sort of measurements and things that have been going on today. But to make a valuable company to exploit these, that is nowhere near even the tip of the iceberg, for 2 different reasons. One is, you'll never get any value out of just selling these. If you sell these for a few euros a piece and make 1,000 a year, you won't make a business out of that. The value comes up here when you're generating data, solving a problem directly. So there's a value part of why you need to do so much more. And the other thing is to engage a customer. If someone says, I've got material with a D33 of 150, people in this room might get mildly excited, but nobody in the real world will care, even remotely. To be able to show benefit, you need to show a direct benefit. So for example, if you can put a simple device on a pipe and you show your customer that it's got the benefit to save him money or make his operation safer or improves efficiency, then they'll get interested. So these are really where we're operating at the moment. This is where we spent our really the last 5 years of our time, and this is where it's easy to get into quick markets. But nuclear, oil and gas are on our horizon. Certainly in the UK, there's an awful lot of funding for nuclear type projects, with a major revamp of nuclear power station systems in the UK aimed for 2040. And aerospace and automotive are also on there as well. The barriers to commercialisation are manyfold, and I'll go through those in detail over the next few slides. There's moving from a university lab into a business which can make the same thing time and time again. ISO certification, Six Sigma, longevity, all those things. And moving from simple materials into complex devices, value generation engagement, such as I talked about a couple of slides ago, how you deploy these type of things, and lots of certification and proof testing as well. So this is really where a small company like us needed an investment, I think, because without that you're never able to make the jump into the sort of sonic tolerances and performances that Morgan and Meggitt perhaps take for granted after the amount of time they've been doing it for. That's really what we're doing over the next 24 months, is setting up those sectors in volume. Really, long-term testing is key. So if you want to do some quick testing at 300 degrees centigrade for 10 minutes, you can do that with Piezo-T. People are using Piezo-T much hotter than I think perhaps everyone realises. But if you want to have a sensor sat on an oil pipe looking at a weld, and you want it to work for 10 years, you're going to have to prove that it's up to the job. And the only way you can do that is to get stuff under test for long periods of time. And this is some provisional results from that. So this is similar data to you've seen before for one of our materials showing KP and D31. And that doesn't mean too much for various clients. What's perhaps more useful to lots of people is to look at how these things age at temperature. So we've got a number of furnaces and ovens, and what we do is we wrap the things in foil to short circuit the electrodes, put them in the oven for a certain period of time, and then start to look at how the deterioration occurs. It's quite a lot of scatter there, and that's quite interesting what we've heard here today. These are just burning core measurements. Pretty big scatter on the results that you get there. But it allows us to show that we've got conventional piezoelectric aging when we look at the drop in performance as a function of time. So this is just 30 days, but that gives you an idea of where you might be in 10 years' time, as long as there's not another failure mechanism comes to play. So we'll be down to about 79% of our original piezoelectric activity after that period of time. The other thing that's useful to look at this, and it's useful where this consortium provides big value, I think high temperature materials are always, by the physics, going to have a much lower piezoelectric activity than Piezo-T. So Piezo-T has got a D33 of 400, 500, and high temperature materials such as ours are much lower. But when you look at the performance of these materials at the temperature which they're designed for, you start to see the properties, are something like Piezo-T again. So if you compare that value there and that value there for D31, you've got almost a threefold increase in activity. So I just want to really walk through perhaps some of the difficulties of going from a materials science type piece, where our core IP is, to being able to generate devices and being able to engage with customers. This is just a simple noddy sketch which I put together of a conventional transducer. You can buy these on the internet for about 100 quid. This would be a simple means by which you might use ultrasound, maybe at 2 or 4 megahertz, to detect a crack in a body. So this is the basis of non-destructive testing in things like rails or pipes. So the transducer, there's a quick pulse, and there's an ultrasonic wave, leaves the transducer, detects the floor, and then there's a coax on the top, and you tell us something about what you've got going on. So there's a transducer, there's a couplant, this is steel, that's steel, if there's any air in between, the acoustic energy never leaves this. So, for example, in medical ultrasound, this is exactly what the silicone gel's there for, to couple the human body to the medical ultrasound equipment. But there's a lot more going on in there, and this is really where Onyx has spent a lot of its time and money over the last 2 years, is solving a lot of these problems. So inside the transducer, this is a piezo that we all know and love. There's a front face on there, but many of these things to work at room temperature are taken for granted. There's vast amounts of information out there on how you do this to work at 100 or 200 degrees centigrade. But to do this at 350, lots of things have got to change. In this list here, I've just provided examples of how one would do this for a room temperature device. So electrical connection to the piezo, you could solder it on, or you could have a mechanical fixture. This backing material, which is all this space here, is conventionally tungsten loaded epoxy. The properties of that are that it must have the same acoustic impedance as the piezo, so that the energy going backwards goes into it, but then it scatters it. So essentially, a composite with the same product of the impedance as the Piezo T. But you can't do that at high temperature. We tried this for a laugh. What happens to tungsten when you get it to 400 degrees centigrade? You nearly set fire to your lab because it turns to tungsten oxide in a big pile of green stuff. Bonding, you can't use epoxy and gels. There are lots of high temperature adhesives out there on the market that claim they'll work at 350 degrees centigrade, but they don't. All the properties at high temperature are so poor. It's like having a runny liquid in there, very poor. Insulation at high temperature, people still use cork. Cork's very good to go down the outside here, to stop coupling with the body. And the couplants at the front end, often water or glycerol is used. So that's really where I think we focus a lot of our energy. To make these materials work at high temperature, to prove that they work, we've had to solve a lot of these issues. And then the next level of complexity to be able to engage with customers is how do you get your devices into the operational sphere. This is just an example. There's a hot system there. There's loads of lagging. If you're looking at a weld between perhaps this pipe joined onto that body, the last thing the customer's going to let you do is come along and drill holes into the thing. You know, you've affected it. If this is a 3-foot perimeter, you can't suddenly put Jubilee clips around it and attach things. There's lots and lots of considerations to work at high temperature which need consideration. And I think the third big thing to overcome is proof testing and approval. ATEX, all this stuff down on the right hand side. Sorry, I've destroyed that. Intrinsic safety. Piezoelectrics at high temperature cause a huge problem for lots of reasons. The first of which is the pyroelectric effect. The biggest electric shock you'll ever get in your life is when you take a piezo off a hot plate and put your finger down the outside. You can generate huge amounts of energy. You can generate a blue spark across the surface. So if you want something to go down a hole 2 kilometres down in an oil and gas environment, you've got to make the thing intrinsically safe. And that's quite difficult to do at high temperature, because typically you might use a Zener diode or some low temperature application. For aerospace in particular, they want to know all the possible means by which it can fail, and they want to know what you're going to do about it. Often in aerospace, for an ultrasonic device, you'll see a dual lane. You'll see a means by which you can have complete redundancy of one of those devices, and it will still work. And the other I talked about earlier, which is there's nothing better than long-term testing. Get it working in the environment to which your customer will actually use it for 6 months and prove it. These are just quick case studies, just some work we've done previously to put this in perspective and perhaps show the value to the customer. So the first one was really sensing steam in a pipe at 350. Before I met the customer, they were using Piezo T. To be able to put this on a pipe, to make the Piezo T work, they had a long standoff essentially, lovingly called a waveguide, but it was just a long metal stalk. Downside to that are, 1, it's bulky, you can't put it through packaging or through insulation. 2, you've lost loads of signal. And the third thing is there's actually things you can't do. If you're looking at Doppler shift and angled flow, the beam shape of the ultrasonic signal that comes out, you're quite limited to what you can do. So we developed a system, there's a simple piezo in there that allows you to put this directly on a steam pipe, and this is just some simple provisional data that we're able to show. You can suddenly pick up the steam. So the customer does, this is just AC noise, but when you've got the steam going through, you get a lot of extra signal, Fourier transform on that, and lots of complex analysis allows you to convert that directly into a steam flow in meters per second. The next one I want to show you is crack detection. How have we overcome those challenges? And there's lots of different ways you can do this. I think always with high temperature applications with piezo, I think what we've come across is there's more than one way to skin a cat. If you're looking for a crack in a metal pipe, you've got magnetic systems, there's Hall effect probes, there's EMATs, but there's lots of oil and gas still, they love to have you irradiated source and a scintillator. It works very, very well. It's becoming more restriction now, but it works very well. But you've got lots of options as well with Piezo T. So you could use Piezo T for a short time, for example. People still do this at 350. You could use Piezo on a standoff, which I've just mentioned, or you could use Piezo2 with a water-cooled system. Or the best alternative, the most viable, is to use a high-temperature Piezo. This table's a bit busy, but it just perhaps shows you a few examples of this. So, short exposure, you could do it tomorrow. You go and buy a probe, you chuck it on a pipe, you see if it works. The downside are, it can be quite wasteful. It needs manual intervention. You need a guy or a robot to go up there and do it. So it's not continuous processing. You can have a waveguide, they're readily available, but it's expensive, it's bulky, and there's lots of IP around this as well. The waveguide manufacturers have locked an awful lot of this down. Water cooling, again, you could do it tomorrow. But it's bulky, it's not elegant, and you've got so many different things that go wrong. If you've got a hot plant and you've got water whizzing around, what happens if the pump breaks? The elegant solution is high temperature Piezo. Flexibility, size. So phased arrays are becoming the next an important thing now for high temperatures. Lots of projects in Europe on high temperature phased arrays now. Conventional Piezos have got much lower activity than Piezo-T. I know D33 isn't necessarily the figure of merit here. There are lots more complex, important things, the coupling and so on and so forth. You've got high temperature electrical connections and acoustic interfaces, but it's what we believe is the way forward. And these are some initial results that we've done. We've got some UK money really to allow us to develop our next range of prototypes. This is a simple gadget on the top right hand side which has got some biomaterial in there. There's a high temperature wire coming out the back face. This is the acoustic front end, Piezo just behind that. And all we've done here is we've put our material against Piezo-T head to head just to look at some speed of sound measurements in a piece of steel. As you do one cycle up to 350 using Piezo-T, it's dead. It doesn't recover. Sorry, my headphones are falling off. But this is a 10 cycle using our proprietary ionics materials. You heat it up and you cool it back down and it recovers. This gap here in the sensitivity is simply because of the attenuation of the stainless steel increases so much as a function of temperatures. It's well recorded in literature. And this just shows you a simple signal. This is the ring temperature signal. This is a wave-generated reflection from a 10 nanosecond top hat voltage distribution on the Piezo. We get some loss of signal at high temperature, but that's more than enough signal to start working with. That's bare signal without any signal processing or anything like that. So the challenges are, for us, is to lock down the Piezo manufacture a lot more and to continue to work on our high temperature solutions. We've now got bespoke solid couplants and backing. We've done a lot of that. We've solved a lot of those issues. And we're building and developing further our capability to design and test devices. So, we've engaged in a number of partners and we're in a situation where we're trying to define new markets. I just want to show you a little clip at this point. There are lots of other benefits to the materials we've developed as well, other than high temperature. Mainly these are around strength and toughness. I think the extreme markets that we're looking to attract, temperature is a big part of it, but if you're looking for 10-year applications, it's got to be able to survive stress, pressure, lots of things that Tim put up are the main UK deliverables. With strength and toughness come machinability as well. You can make smaller features. So this little video here, which I'm going to play, is an example of the increased toughness that we see in our material. This is a 4-point bend test, and in this are 2 strips of material. Piezo-T, very high density Motorola Piezo-T, hot pressed, and then the ionics materials. And what you'll see is the Piezo-T, when it gets to a strain of 0.2, there you go, is snapped and broken. And then as the jaws continue to move up, which I'm hoping is going on, there you go, you can keep bending and bending. This is 0.2 millimeters thick and 30 millimeters long. And this leads to a strain to failure of 0.5%. They're hugely strong, these materials. And the reason for that enhanced toughness and strength is exactly the same reason that the zirconia is tough and strong. It's because we've understood and controlled the crystal structure inside these materials. So considerations going forward, the electrode's a big issue for us. Silver doesn't work very well necessarily at high temperature. A move to gold involves extra complexity and cost, ease of synthesis. Thermal expansion is a big issue for repeated cycling at high temperature. If you get this right, you can use it to your advantage, because you can clamp the piezo laterally, you can increase some of the piezoelectric coefficients, whilst at the same time increasing the longevity. Getting the packaging right, but if you get it wrong, you've got a massive failure mechanism. And I think it's fair to say good characterisation, to be able to keep control of your process. Measuring these materials at high temperature is not easy, for lots and lots of different reasons. So in summary, there's a big market for high temperature piezos out there, and there's lots and lots of barriers to development, but these can and have been overcome. And there's lots of benefits which you talked about, all that come down to money. But to succeed at that, there's still lots and lots to do. Okay, so I'll finish there. Thank you.